So we've introduced this very simple model of calculating the Earth's temperature based on the input of radiation and the output of radiation, where we have the solar constant, S0, we have the albedo of the planet, how much is reflected back to space, big A. We have this tau, which is the greenhouse effect, the effect of the atmosphere. We have a constant, which is the Stefan-Boltzmann constant, and the temperature of the surface of the Earth. Now we're going to actually look how these parameters vary spatially on the Earth. Until now we've spoken about one number for each of these parameters, but let's see actually how they vary spatially around the planet. So first of all, the income radiation. As we said, if we look at a percentage of 100% coming in at the top of the atmosphere, we've already spoken about the albedo being 30% on average. That 30% we can break down to reflection off the surface, which is about 4%. The scattering through the atmosphere, what gives us the blue skies, we lose about 6% of that radiation. But most of it is the reflectance from clouds. Clouds are bright, white-colored. They cover more than 50% of the planet. We'll speak more about clouds later on in the course. But they are the major factor of the albedo of the planet, the reflection from clouds, which are actually preventing this radiation coming in. Some of it is absorbed also in the atmosphere. About 19–20% of the radiation gets absorbed in the atmosphere. And only around 50% makes it all the way to the surface and is absorbed at the surface of the Earth, in the oceans, in the soil, in plants, at the surface. 51% makes it all the way down from the 100% that started at the top of the atmosphere. And again, if we're looking coming down the insolation is the solar radiation, the watts per square meter coming in. The atmosphere has a role of scattering. Again, the blue skies are because we're scattering the light and some of it leaves the atmosphere going back out. Some gets absorbed in the atmosphere. Some will come all the way down to the surface and will be reflected off the surface without affecting the temperatures. In other areas, we'll have absorption at the surface. So it's actually quite a complicated process coming from outside the atmosphere through the atmosphere, being absorbed, reflected at different altitudes, and eventually being absorbed and reflected also at the surface. So here's a map of the albedo of the planet. If we look spatially at the values of the albedo, and that's again the big A in the equation. And the color bar here represents the percentage of the albedo. Again, albedo is measured in percentage from 0 to 100% or 0 to 1. So the bright areas here show you where we have the maximum reflectivity out to space. And this occurs normally where we have ice, for example, over Antarctica, over Greenland, over the North Pole. We have ice over the oceans there. And as we go to the tropics, where we may also have less clouds and dark oceans, we can see the blues are where we have less reflectivity out to space. So the albedo, the average of the planet is 30%, but it varies quite dramatically with latitude, but also with longitude. And you can also see that, for example, over the Amazon jungle, we actually have brighter colors, which means higher reflectivity. We also can see this kind of horizontal line of higher albedos. And we'll talk about this later, but these are related to clouds. Although the rainforests are very dark and absorb a lot of radiation, when we're looking from the sun sees clouds and thunderstorms covering the Amazon, and so a lot of the sunlight gets reflected back to space. We can also see the Sahara Desert, which has also got high albedos, not because of clouds, but because it's very dry and the surface is very bright yellow color compared, say, to the forests. So we can see differences here due to surface changes, atmospheric changes, and latitudinal changes, with the highest albedos being also due to the angle of the sun, which is hitting the surface, which changes with latitude. So if we look at the solar radiation, making it all the way down to the surface, here we can see that now this is looking at the S0. On average, we have 1,362 watts per square meter, but that also varies as a function of latitude, longitude. As we expect, the sun is much more vertical to the surface in the tropics, close to the equator, so we will get higher concentration of energy in the tropics. As we go to higher latitudes, to the pole, the sun is at much a higher angle, and therefore there's a lot more reflection off the surface, as well as we're having higher albedos there. But here too, we can see horizontally over, say, Africa, these areas where we have less radiation making it to the surface, and some of these areas in the tropics are again due to clouds. Clouds are blocking out the sun and are causing the reflection of the sun out to space. So when we measure at the surface how much radiation is making it to the surface, we actually have less clouds, less radiation in these regions because of the cloud cover. Just to point out again that as we go from the tropics to the poles, the angle of the sun relative to the surface changes. If we look at the rays coming from the sun, we have the same amount of radiation everywhere. Again, if we look at perpendicular to the rays, for every square meter, 1,362 watts per square meter. But when it hits the surface, you can see what happens at the poles. That amount of energy gets spread out over a much larger area compared with what happens in the tropics, where it's basically perpendicular to the surface. And so we have less, for every square meter in the polar regions, we're going to have a lot less energy than we do in the tropics. So looking at this equation again, how can we change the Earth's temperature based on this simple equation? So one idea is we could change the albedo, the big A in this equation. And this happens quite often. I wouldn't say quite often, but it's happened over decades and centuries on the Earth. And these are volcanoes, which can put basically a haze of very small particles in the upper atmosphere. And the last big event was in Pinatubo in the Philippines in 1991, June 91, a huge eruption in the Philippines, which sent gases and particles way up into the atmosphere, 20, 30 kilometers above the surface. And these particles eventually caused a very thin kind of mist of particles in the upper atmosphere, spread completely around the planet, and caused the Earth's temperature to cool by nearly 1 degree for a number of years. And we can see in the bottom plot here both observations and a simulation, which show the red line represents the time of the eruption. 0 is the temperatures, or the reference temperatures before the eruption. And we can see that both the model and the simulation show a decrease of up to 0.8 degrees globally, which reached a peak actually a year or so after the eruption, because it takes time for these particles to spread around the whole planet to block out the sunlight. Eventually they fall out of the atmosphere due to gravity, but it takes a long time, and it can take a few years. But when they do fall out, then we'll return to the normal temperatures, as you can see what happened in 1994, 1995. But for a number of years, we actually changed the albedo of the planet and cooled the planet. And so if we actually increase the albedo, if we change the A from, instead of being 30% to 31%, 32%, you can actually put the numbers in and see how that affects the temperature of the planet. Now let's talk about the outgoing radiation and how this is distributed spatially. So again, here it's fairly complicated. We're talking about the heat which is being released from the Earth, from the surface of the Earth. This has to go through the different layers of the atmosphere. We have absorption by greenhouse gases. We have absorption also by clouds. Some of this makes it out of the atmosphere. A lot of it gets trapped inside because of the greenhouse gases, water vapor, clouds, carbon dioxide, and other factors. So here we can actually see what we call the outgoing long-wave radiation, OLR. And this we can measure from satellites. So we can look down at the planet from satellites and see how much radiation is coming out from every pixel, from every location on the planet. And this color bar goes from about 145 watts per square meter up to 345 watts per square meter. The reds are where we have more energy being released and leaving the planet, which means, as we spoke about the Stefan-Boltzmann law, it depends only on temperature. So the reds are where it's hottest, and you can see the Sahara Desert, where we have the highest temperatures and the highest emissions leaving the atmosphere. And as we go again to the polar regions, which are much colder, T to the 4th power, much less energy being released in the polar regions and over Greenland. And again, we can see the effect, the lighter areas over Africa, over South America. These are due to clouds. Clouds in the atmosphere are much colder than the land underneath them. And so what the satellite is actually seeing is the emission of heat from the clouds. So we see these lighter areas in the tropics or where we have clouds and are actually reducing the emissions. And here you can see this map of cloud cover. This is for a specific month. And it's actually interesting that here we haven't drawn the boundaries of the continents. What you're seeing here is simply the cloud cover on the planet seen from satellite. And we see that there's very large differences, say, between the desert regions in the Sahara, which have very little clouds, so they're dark in color here, to regions of the oceans where we have lots of clouds. And you can see, or maybe you cannot see even Europe on this map, because Europe has always got clouds over it sometime, and so you don't see any significant difference between land and ocean. But Australia, you can see, has less clouds. And again, we can see that in the tropical regions, we get these bands of clouds across the tropics, which we'll talk about later in the course. These are causing high albedo. They're reflecting more sunlight back, but they're also trapping in the heat released from the Earth, reducing the amount of heat that can be released out to space. So on the right-hand side of the equation, how could we change the climate? Well, we're doing it at the moment. The little t or the tau on the right-hand side of the equation is basically the atmosphere or the greenhouse gases. And here we can see the increase in carbon dioxide in the atmosphere from the 1950s, which keeps on going up. So if we now increase the greenhouse effect, so instead of 0.62, we want to reduce this number because we want to trap in more. So the 38% will go up to 39% or 40%. What happens when you put this into the models, you get the global warming that we're already seeing today. And here in the bottom plot, you can actually see the observations over the last 100, 150 years, showing this increase in temperatures, which are calculated by many different groups here. Each curve is from a different group, which has done the analysis with the raw data from different stations around the globe. And this global increase, again, is because we believe, due to the change in the little tau that you see on the right-hand side of the equation, the greenhouse effect on the planet.